Hello, students. My name is Shashank Shekhar, and we are doing the chapter that is solution. So we have started the chapters. Two of the lectures are over. So let us continue this chapter today, right? So this is a chapter that we are having, that is solution chapter. So in this we have seen the various parts. So first we have started the what is the solution and what are the types of solution that we have. Then we have quantified the solution. So what a solution is called means how can we say that this solution is different from same solution but having different number of particles. So we have seen the concentration terms in that. Then we have seen the types of solution like liquids and solids. Solids and liquids and gases and liquids. So two types of solution we have already seen. Today we will be focusing on liquid solution means we are dissolving a liquid in a liquid means the solute and solvent both are, you can say, both are liquid. So this is the syllabus that we have. So this is type of solution we have covered. We have covered expressions of solids and liquids. Then we have seen solubility of gases and liquids, right? We have seen this also, solid solutions. Today we will see Raoult's law. So this Raoult's law mainly deals with the solution that is having both solute and solvent as liquid. Now if you look at the topics of today, so it will be basically starting from the solubility of liquid and liquid, and we will see the law that is governing this solubility, right? Also, we'll see the graph and see how this Raoult's law is relevant to this Henry's law. I mean to say that this both of this law are connected in a way to each other. After that, I will just apply this Raoult's law on the mole fraction of vapor component. You will come to know more about it. What is this vapor component and all? And then we will brief some of the points of solids and liquids, although we have seen it earlier, but we will see a more general application of this Raoult's law in solids and liquids. And you can say Raoult's law can be applied in general to a wide variety of solutions. So let us start our chapter. So the first topic, that is the solubility of liquid in liquid. So what type of liquid in liquid solution now we are talking about? First of all, this should be made clear. So this Raoult's law, which we will talk about, it applies to only a binary solution. Means for now you have to assume that it is applied for only a binary solution, and both of the components are liquids, and not only liquid but volatile liquid. Now what is volatile liquid? So volatile liquid is one which converts very easily from liquid phase to vapor phase. You can say their conversion is very fast. They're easily volatile. So if I talk about volatile liquids, we have our kerosene. You must have seen that if you keep a kerosene filled bowl in open, the kerosene inside it will vanish quickly. So that type of liquid is called volatile liquid. Now, if you take a closed vessel and fill it with a volatile liquid, two volatile liquids actually, sorry, and then what we will see, there is a equilibrium between both the phases. So what I'm talking about is here, suppose I have taken a closed vessel like this, right? And I've filled half of it by a volatile liquid. Now this will form vapor, and it will be like this. It will be present everywhere above the solution. It will be captured by this walls. Now there will be a equilibrium between both these phases, right? Some of this liquid will be going to the gas phase, and some of the gas will be going to the liquid phase. Now if we denote both this component by 1 and 2, so we are saying we have two components, out of which one is having the number 1 and the other one is having the number 2. Now at equilibrium, the total vapor pressure is considered to be P total, because it is containing two type of liquid. So keep this in mind, it is a binary solution. It is containing two type of liquid, and both of these are going to vapor phase. Now the total pressure Now the total pressure will be here. We will talk out only about this vapor phase. Okay, right? So keep this in mind that whenever we are talking about the pressure, we are talking about the pressure of the volatile form. Okay, sorry, the gas form of this volatile liquid, and then the total pressure that is exerted by this vapor form, which contains both component 1 and 2, is called as P total. So we will denote it with help of P total. This symbol will be used throughout. And the partial pressure of this both green one and the red one, that is P1 and P2, the first component, the second component, will be termed as P1 and P2, where 1 and 2 describe the component that we are having. Now, this partial pressure P1 and P2 are related to the mole fraction x1 and x2 of component 1 and 2 respectively. So we'll see how it is connected. So for that, we have this Raoult's law. What we have here? We have here a Raoult's law. So the Raoult's law says that for any solution, the partial pressure of each volatile component, this should be noted. Okay, so this should be noted. It will be used further also. So for a solution, the partial pressure of each volatile component in the solution is directly proportional to its mole fraction. Sorry for this wrong statement here. It will be written as P I directly proportional to Xi. So this is the formula that we have here. So it is saying that the partial pressure of each volatile component in the solution is directly proportional to its mole fraction in solution. So this is the Xi is the mole fraction in the solution, and this Pi is the vapor pressure of the vapor phase that we have seen earlier, right? Now the same thing is written here. The Pi is the partial pressure of the ith component, and Xi is the mole fraction of the ith component. Now two case arises. This you know that this is the formula of Raoult's law, where we have introduced one proportionality constant, that is P naught 1, and it is the pressure of pure component 1. What is this meaning of pure component 1? So it is written here also, pure component 1. It means that by here P naught 1, pure component 1 means that we are having a liquid, sorry, we are having the same vapor that was of P1. So that is a 1, but in the pure form, means only and only P1 one component is present. Then in that case, we will call it as P naught 1. Okay, we will call it as P naught 1. Then what is the second formula here? This one formula we have seen, it is a direct, you can say a direct consequence of this formula. We have just taken the proportionality constant as Py1. But what is the second formula here? That is Pi equal to P total Yi, and here it is written that Yi is the mole fraction of the ith component in the solution. Sorry, in the vapor. Sorry for the mistake. In the vapor. Now, this both formula, you can say they are a result of a Raoult's law only. Okay, so this one is a direct one. This is an indirect one. So what is the main difference with these two? I will tell you very, listen it very carefully. So children get confused in this. The first formula is Pi, P naught 1, Xi. Okay, this is the first formula. And the second formula is Pi is equal to P total Xi. But here it is written Yi. This both thing are same for both of these formulas. It is the vapor pressure due to the vapor form of the ith component. But what about this? So I have told you right now. So this is the vapor pressure of that component only, but in the pure form. Means it is present alone in that case. And Xi is the mole fraction of the component 1 in the solution. So we have two phases. We have seen, since we have taken volatile and we have covered this thing with a lid, so we have taken two phases. So the concentration of both the volatile component will be different in these two phases. So the for the liquid component or the liquid comp phase, we will have this formula to calculate the mole fraction of the ith component. But for the vapor phase, we will take yi, where yi is the vapor pressure of ith component in gas phase or the vapor phase, right? And this is for the solution phase or the liquid phase. So, and we have replaced this P naught I by P total, where P total is the total pressure. Total pressure, that is P1 plus P2, partial pressure due to 1 plus partial pressure due to 2. This is Dalton's law. We will study it more briefly in the next slide. But this one is the most important thing to notice, is that we have taken two formulas and both of these are important. The first one, here we are taking the mole fraction of the component which is in the liquid phase, and here we are taking the mole fraction of the component, same component, but it is in the gas phase. Here P total is the pressure, that is Pi, sum of Pi, you can say P total is sum of Pi. I goes to 1 to n, where n is the number of component. And here P naught 1, you can say it P naught I also, because we will take the vapor pressure of the same pure component that we're talking about. Okay, now if we move to the Raoult's law graph, so children must have seen this graph, and it is very significant to understand this graph wholly. What are the each of this plot saying, axis saying about? What is this going from left to right? Why it is written P1 P total equal to P1 plus P2? You should be aware about all of this. Now, according to Dalton's law, we know that the total pressure over the solution base in the container will be the sum of the partial pressure. So suppose we have two type of component, 1 and 2. So the total pressure will be P1 plus P2. So this is the Dalton's law of partial pressure. For those who don't know, you should be remembering this one. Now suppose we have taken the case that P02 is greater than P01, means that if we are taking component 2 in the pure form and we are taking the same volume of component 1 in the pure form, and we are measuring pressure of both of this independently, then we will see that P02 is greater than P01. So we have taken just a case. There is nothing to think about it. We have taken a case where P02 is greater than P01. Now suppose we have started from here such that we have only x1 present. So the mole fraction will be 1, because total number of moles is 1. Suppose the total number of moles is x and the total number of moles of one first component is also x, and since there is no x2 present, no moles of 2 present, we will write it as x by x, which will give us 1. So initially we have only first component present in the solution, and the concentration of the second component is 0. So it will have x1 as 1 and x2 as 0. Now, as we are introducing this x2, which is having a greater partial pressure, our graph will start to rise, right? And what we are doing, we are introducing x2 and we are introducing component x2 2 and removing component 1. So as we will do this, the mole fraction of 2 will increase and the mole fraction of 1 will decrease, right? So this will the total pressure will also increase, because now x2 is present in excess, and as it will increase, and I have told you earlier that P02 is greater than P01, and it will have a direct effect. So as this 2 will increase, the total pressure will also increase, and at last we have only second component. So the total pressure will be equal to P02. Here we have the first component mole fraction as 0, means no one component is present, and here no two component. So number of 2 is 0 and number of 1 is 0. So this is the Raoult's law graph. So you can see here directly that as we are increasing the mole fraction, we are increasing the pressure effect. Okay, right? So this is the graph. So this was only the Raoult's law. Now, from Dalton's laws of partial pressure, we can write that P total equal to P1 plus P2, where P1 is the partial pressure due to 1 and P2 is the partial pressure due to 2. Now, what we will do, we know our formula P1 equal to P naught not 1 x1, and similarly P2 is equals to P naught 2 x2. Now, I have told you in the first class, very first class, that for a binary solution, we have x2 plus x1 is equals to 1, or xi, if we have ith component starting from 1 to n, then it will be equals to 1. But since it is a binary solution, I will go from 1 to 2. So we'll have P1 plus P2. So we have two components, P1 and P2. So if we add the partial pressure due to both, then we will get the P total. Sorry, if we add both the mole fraction x1, x2, we will get 1. So we can replace this x1 by 1 minus x2. So if we take this one, we can write this directly, right? So this is 1 minus x2 p naught 1 plus x2 p naught 2. Later on, what do? We take this thing here. What we're doing here is that I'm writing it clearly. We will get this thing. So both have x2 in common. But what we can write, that x2, so here is x2, here is also x2. So we can write that p naught 2 minus p naught 1 is multiplied by x2. So here is the thing. And we get p total as this formula. So this is a very important formula. You should remember this. Next topic is somewhat interesting. So we have studied Raoult's law and we have studied Henry's law. Now you see that how Raoult's law is just a special case of Henry's law. So we have studied this Raoult's law. So according to this Raoult's law, the vapor pressure of a volatile component in a solution is given by Pi xi P naught I. So this is the formula that we have for the Raoult's law, where xi is the mole fraction due to ith component and P naught I is the vapor pressure of the pure component. So this is our Raoult's law. Next, we have our Henry's law. What does Henry's law say? That the solubility of a gas in a liquid follows Henry's law like this: Pi is equals to Khx. And I've told you earlier that this Kh is specific and will change accordingly what type of, on or depending on what type of solution we are taking. P is the partial pressure of the gas in the solution, sorry, Pi, and Kh is the Henry's constant, right? So this is the formula of Henry's, and this is the formula of Raoult's law. Now, if you compare both of this, some things are similar. We have our x1, we have our x1, right? We have our pi, we have our pi. Here also x1 will be here. So do not get confused. It will be xi. Okay, this will be xi. So here we have xi, we have xi, we have pi, we have pi. So analogy is somewhat been shown here. So after comparing these two equations, we can say that Kh is equals to P naught I. Okay, so what is Kh? Kh is equals to P naught I. In Raoult's law, Kh is replaced by P naught I. Okay, so this is a type of formulation of this Henry's law only. And it is a special case of Henry's law, in which we have P naught I in place of Kh. Now we'll talk about the mole fraction of the vapor component. So we have seen this formula earlier also. So we have told that Pa is equals to, if we are talking about the eighth component, then we'll write it as P total YA. So if we take this PA here, sorry, yeah, PA equal to YA P total. Now if you want to write this YA, you can write it as PA divided by P total. Yes, it is right. The same thing is written here. Similarly, if we take YB, then what it will be written? It will be PB is equals to YB P total. Then we can write YB as PB by P total. Here it is also written same thing. Same thing is written here also. Now we have seen earlier and we have seen it right now in the previous slide. Then we can write PB is equals to P naught B plus XB. Here the Y we are talking about, it is the mole fraction of the eighth component in the vapor phase. Okay, so do not get confused with it. And the X which we are talking about earlier, XA, so that was the mole fraction of the eighth component in the liquid phase. So if we replace that PB with P naught B XB and PA with P naught A XA, we will end up getting this result. We will write it like this. And here also. P total YA. And P total YB. So we have written this same thing here. Now we have two conditions. So sorry, two formulas. So if you want to write P total, how you will write? We will write it as, sorry, here. So I've used this formula here to convert this to this. Now, if what do? We know that P total is equals to PA plus PB. Okay. So we know this formula. We have seen it earlier. Right now, that we have replaced XA by 1 minus XA and we got this P total is equals to 1 minus XB P naught A XB plus P naught B. Now, since both of these are containing XB, I can write P naught A plus XB into P naught B minus PA. Now, how I will write this XB here? So let me write this first. P total is equals to P naught A plus XB P naught B minus PA. This is our P total, right? This is our P total. So if we simplify it further, we will write it as P total minus P naught A. So I move this on this side is equals to XP P naught B minus PA. So we can write further XB is equals to P total minus PA by P naught B minus PA. So here it is written same thing, that XB is equals to P total minus PA by P naught B minus P naught A. Now what are we doing here? We are putting this XB in the above equation. So we have seen this equation, right? We are putting this XB in the above equation. So we will write So this is the formula that we have. We know that PB is equals to Y total, sorry, YB P total. Okay. So I'm replacing this YB with this. Okay, so we are taking this equation which says that XB P naught B, sorry, XB P naught B is equals to P total YB. P total YB. So we will replace this XB by this thing. So we'll write it as P total minus P naught A, P naught B minus PA. So it will be equals to P naught B and P total YB. This is the equation that we will get. Okay, so this is the equation that we get. Now what we will do, we'll try to simplify it more. What we will try? We will try to simplify it more. So how we will simplify it? How we will simplify it? So let us see. So let us first write this equations once more. So it is written as P total YB is equals to P naught B P total minus P naught A, P naught B P total minus P naught A divided by P naught B minus P naught A. P naught B minus P naught A. So what we have to do, we have to take this P total out of this. Okay, so what we have to do, we have to take this P total out of this. So how we'll do it? So we can write it as P total YB is equals to P naught B P total by P naught B minus P naught A. Similarly, we can write it as P naught A P naught B is equals to P naught B minus P naught A. So if we take this thing here, it will be P total is equals to, sorry, P total YB minus, if you put it here, we can write it again, minus P naught B P total by P naught B minus P naught A. So it will be written as P naught A P naught B by P naught B minus P naught A. Yeah. So I bring this thing here, it will become this. Now I will take this P total common. What I will do, I will take this P total common. So it will become P total YB P total YB minus P naught B by P naught B minus P naught A. Okay. So this will be first. Here will be P total will be taken common. We will get this. And here what we will have? Here we will have minus P naught A P naught B minus P naught A P naught B by P naught B minus P naught A. So this thing we will get. Now we'll simply divide this both of these things. So if you multiply it here, what we will get? We will get P naught B YB minus P naught A YB minus P naught B like this. P naught B minus P naught A. And it will be also P naught A minus P naught B multiplied by each other by P naught B minus P naught A. This both will get cancelled. Now if I want to add P total, it will be finally P naught A P naught B by, I am taking this minus sign here. It will be P naught A YB minus P naught B it will be also in plus minus P naught B YB. If I take just the reverse of it, it will become 1 by P total is equals to P naught A YB P naught A YB by P naught A P naught B. Right? Then we will have plus P naught B by P naught A P naught B. At last, we will have P naught B YB P naught B YB by P naught A P naught B. So this will get cancelled. This will also get cancelled with this. And you will get this thing at last. YB by P naught B minus YB by P naught A plus 1 by P naught A. And what is this? So if you write it, we can write it as 1 minus YB by P naught A. So we can write it as 1, you know that YA plus YB is equals to 1. So we can write that YA is equals to 1 minus YB. It is very clear from the start. So final equation will be YB by P naught B plus 1 minus YB is YA, so YA by P naught A. So I've done a very, you can say a very complicated not, you can say an easier transformation of this 1 by P total in terms of YA by P naught and YB by PB. Yeah, it will also have not here. Sorry. So we can write our P total in terms of this thing YA by P naught A by YB by P naught B. So this is the final equation that we got. So it was a long calculation, but it is worth it. Yeah. So if you are given, say pressure PA and PYA, so you can just calculate the YB if you have your P total and P naught A, P naught B. So it is a very good practice to do this. We can have one more formula if you want. So if I write this YA, it will be number of moles of A by number of, sorry, it will be number of moles of A by number of moles of B by number of moles of A. And this all moles are in the gaseous phase, right? We can write this also. So if you just plug this from Raoult's law, that is Pa equal to P naught X, and try to do it, you can derive with another formula. But that would be not that much of that much important. But this is a good formula if I tell you this one. That 1 by P total is equals to 1 by YA by P naught A plus YB by P naught B, where 1 by P total is inverse of the total pressure. YA is the mole fraction of the component in the gaseous phase of the A component divided by the pressure that will be applied by A in its pure form. Add, you can say sum YB, YB which is the vapor pressure of B in the, mole fraction of B in the vapor phase, and P naught B is the vapor pressure due to component B in the pure form. Now, if you want to generalize it, you can write it as, for any component system, 1 by P total is equals to, what it can be written? Summation of I is equals to 1 to N YI by P naught I. So this is the final equation that we are looking for. Now, I will talk somewhat about the solids and liquids. Although we have seen this solids and liquids earlier, but we will talk more about this. What we will talk, we will just try to quantify it. So earlier we have just qualified it. So we have done a qualitative analysis. We have said that, okay, when we will decrease the temperature, the solubility of solids will decrease because it is an exothermic process. And similarly, it is an endothermic process. And similarly, if we increase the temperature, then the solubility will also increase. So we have told this thing earlier. Now, second, I have told that, okay, the pressure that we are having, will have no effect of the solubility of solids in liquids, but we will simply change it to some extent. So suppose you have a solution of solids and liquids, which can we have sodium chlorides in water, or iodine and sulfur in carbon disulfide. Now, each of this component, the vapor phase of this solution differ from pure solvent. Yes, it will be true. So the water will have a greater vapor pressure than the solution of sodium chloride in water. Why is it so? So in this case, we are telling about those solids which are non-volatile, because we don't see volatile solids often, but we just see only those solids which are non-volatile. So we are adding, suppose, a non-volatile solid in liquid. So the solid which is non-volatile in nature will be the solute, and the liquid which is volatile in nature will be the solvent. So before the addition of the solid, we have this kind of condition. So we have put a lid upon this, we have our pure solvent. Now this component here is going in here and it is applying pressure on this interface. And the number of particles that can go is available here on the top surface. Now what we have done, we have added a non-volatile substance to this solution, which gives a kind of this scenario. So you can see very clearly we have one non-volatile solid, then we have volatile solvent, or you can say we have non-volatile solute, that is solid, and we have a volatile liquid solvent. Now it has occupied some of the positions here. So whether you say this position or this position or this position, now they are occupied. Now the number of gaseous particle has also been put down. Why is it so? Because adding a non-volatile solute reduces the vapor pressure of the solution. How? By increasing the number of components on the brim. So now the vapor pressure that is exerted on both on this surface, or you can say on this interface, is less. Why? Because we have introduced non-volatile solid particle. The same thing is written here, that the surface is covered by both solvent and solvent, reducing the mole fraction of the surface occupied by the solvent molecule. Means the fraction of molecules that are present on the surface has been reduced because of the addition of solids. Next, what we will do is we will apply this Raoult's law in a more general form, or you can say I will describe Raoult's law in a more general formula. So what it is written about. So if I talk about the Raoult's law, I have told you earlier that if we are taking two volatile liquids, so I have told you earlier also that we will take volatile liquids only, then the partial pressure due to the ith component will be directly proportional to the mole fraction of that component in the solution. So this thing I have made you clear. And the point that I told you to keep in mind is that the component that we are adding must be volatile. So this should be in your mind always, that the component we are talking about is always volatile. So if we take a general case and try to quantify every solution that we have around us which is having a volatile component and wants to say there or mention there or state their mole fraction in the solution, then we can do it until and unless it is volatile, then only. Means here we have an example here. So we have taken a graph, right? We have this solvent X and we have a vapor pressure of the pure solvent. Now initially we are having only 0 mole fraction of the solvent. Means the other non-volatile substance is only present and the solvent which is volatile in nature is present in 0 concentration. So due to this we have a vapor pressure of 0. Means the P total is 0. Now what I have done is I have started adding volatile solvent slowly. Means the mole fraction of the solvent will increase. Yeah. So you can see here we have a increase in the mole fraction of the solvent in this direction. Now what will happen? As I have told you earlier that the Raoult's law can be generalized as, so if you have a volatile component addition, then the vapor pressure will be increased. So the same thing is happening here also, that the vapor pressure starts increasing like this. Okay, so you can see here that the vapor pressure has increased for the solvent 1. Sorry, for the solution due to the solvent 1 that is added right now. So we have generalized this thing and we have written the Raoult's law, which says that P1 is equals to, or you can say directly proportional to X1, or we can write that P1 is equals to X1 P0. So this is a general formula of Raoult's law. Now, if I want to summarize this whole class, we can say that we have seen liquids and liquid solution, right? We have seen liquids and liquid solution. Then we have seen that, okay, we can justify or quantify it using Raoult's law, which says that for any two volatile liquid which are added, and we are talking about binary solution, then the partial pressure is directly proportional to the mole fraction of that component in the solution. And we have introduced one proportionality constant, that is P01, which is the pressure due to the pure component. It's the same pure component whose partial pressure we want to take in the solution, right? So this is the thing. It was Raoult's law. Then we have a more formula which is you can say an analogy of this Raoult's law, and it says that the partial pressure is also proportional to the mole fraction of the gaseous, right? Because it is the gas only whose partial pressure we are calculating, so it is directly proportional to the mole fraction of the gaseous molecule that is present in the lead, or you can say the container. And we have introduced the proportionality constant as P total, where P total is the total vapor pressure due to all the component that is present in the solution. So if we are talking about binary solution, then we have P1 plus P2. Okay, then we have P1 plus P2. So this was about a general concept, or you can say extension of this law, Raoult's law. Now I have shown you some formulas. Means we have some formulas like this. So this is the first formula that we have seen. So these formulas are important. So try to derive it by your own, on your own. So try to derive it by on your own. So it will be helpful for your calculations also. The first one is for the P total, which is P01 plus P02 minus P01 x2. Then we have this important formula here. Okay, write this thing. Which says that 1 by P total is equals to the YA by P0A plus YB by PB. We can have P0B, sorry. We can have YC by P0C. Again, then I have told an extension of this, or you can say a quantitative analysis of this solids and liquids, which I have done it using the Raoult's law, which says that if we introduced a volatile component of this, then the pressure due to the volatile component of the vapor phase is directly proportional to the mole fraction of that component, volatile component. And we have introduced a proportionality constant, that is P01, that is the partial pressure due to the component 1 in its pure form. So this was all about today's lecture. So thank you for your time. We will see tomorrow the rest of the remaining things. So we'll start with the ideal solution and non-ideal solution. So we are left with this only. Then we will see the colligative property. So this is, you can say, the colligative property are a much more dependable thing for obtaining marks. But you should be knowing this all. They are like our tool. So it will help you in those, or you can say in those understanding those colligative properties very well. So this laws, we have started from the Henry's law. We have also seen Raoult's law and applied our Dalton's law of partial pressure in some sense, which says that the total pressure is equal to the partial pressure of each component that is present in the solution. So this was the thing we study right now. Now we will see, I have finished this colligative property and our chapter will be over. So thank you for your time.